Hey, everybody. Good afternoon. Good evening. It is exciting to see an audience back in person in Oslo. I've attended and spoken at the event a couple of times before. This is my first time virtually, which is a bit of a bummer. I wish that I could be there with you all, but I'm very excited to see the event taking place in person again. And hopefully I can join everybody next time. But I'm excited to share today my thoughts on Python, the programming language, on just the excitement that I have and many have around working with Python on embedded and IoT devices. So hopefully it should be a good time. Real quick, my name is Brandon Satrom. I'm the Vice President of Developer Experience at Blues Wireless. I'll share more about who we are, but Blues Wireless is an IoT product and services company, and we are focused on transforming the way that developers build connected solutions. So I want to talk about Python today and give you my perspective on why I think Python is such a powerful language and why it matters in the world of embedded development. I'll start with a bit of history, talk about some of the flavors of Python available on devices, and mix in a few demos as we go along. But first, I want to start by stating why I think Python matters. And you may be here today as someone that uses Python day-to-day in ML. You may be a data scientist. You may be a Python programmer working on other aspects of the language, and you're interested in embedded, and maybe Python is a way for you to get there. But you may be coming from the other side of the house. You may be an embedded engineer that is comfortable in C and C++, and you're skeptical of why I would share this language as a valid opportunity or a valid option for working with embedded and IoT devices. And so I want to frame this part of the conversation by really talking about complexity and why this matters for many of us, because a lot of the software and hardware world really revolves around what we do to get the job done, how we can actually deliver products. And you know this well. If you're working on a site or an app, or you're working on a giant ML project, there are a number of things that can trip you up and slow you down. And this is especially true in the hardware world, where in addition to dealing with all the bits and bytes in the software world, we have to deal with the existence of atoms and the complexity of the physical world when we're dealing with sensors and actuators and batteries and power and connectivity and all of the different things that really make or break a project. It's all complexity. It is true in software, it's true in hardware as well. And when I think about complexity, I tend to think about a quote from Ray Ozzie, who is the CEO and founder of my company, Blues Wireless. And that quote is, "Complexity kills. It sucks the life out of developers. It makes products difficult to plan, build, and test." I'm guessing that many of you have heard that one, because it's something that Ray said many years ago in his software days before starting Blues Wireless. But even if you haven't heard it, I'm sure it resonates, right? Complexity kills. I feel like a lot of the work that we do as engineers day in and day out is driving out complexity to be able to actually build things and get to the solution to a problem. And in the embedded world, part of that complexity lies in languages for many of us. And in the embedded world, if you haven't worked in this space for the last several years or so, there hasn't been as much language innovation as there is in the desktop computing world. Part of that is because of the constrained nature of many of the devices that we work with that are out there. If you're working on a PLC or a PIC-based system in an industrial setting, you don't have a lot of memory and space to work with. And even if you picked up this entire world in the early Arduino days, where the Arduino Uno was basically just effectively an 8-bit computer, there wasn't much to deal with in terms of RAM and flash available. And so we worked at a low level with very low level programming languages, much like in the early desktop computing world. And I'm not here to criticize C and C++ or make a joke at their expense. I actually like those languages a lot, and I use them almost every day. Part of the nature of being in this embedded world is that you tend to kind of bounce between a lot of different languages. But the reason that I bring this up is because C and C++ aren't for everyone, and the learning curve of these languages is quite steep. And so when it comes to considering a programming language for the future in embedded systems, we really want to look at the opportunity that's out there and consider that businesses around the world are anticipating the need to deploy billions and billions more embedded and connected devices in the coming years. The reality is that even though IoT, edge computing, whatever it may be, is a buzzword that's been around for a long, long time, we're really only at the beginning of what we anticipate seeing in terms of the number of things that we bring online over the coming and ensuing years. And all of these devices, all of these applications need developers. They need many more developers than those working professionally with C and C++ today. The opportunity is much bigger, and there's a lot of people interested in pursuing that opportunity, and there's not a ton of existing engineers and resources out there that can work to really meet that demand. So the question becomes, what are our options as an industry? If we want to enable the next 50 billion embedded devices, and that's probably a conservative number, what are our options? Do we insist that C and C++ are the only path through the door, or do we try another approach? Now, you may point out to me, if you're a C, C++ aficionado, that according to the TIOBE index for August of just this year, in 2021, C is still the most popular programming language, according to their ratings, and C++ is at number 4. And you'd be right. By that metric, that's true, even though Python did move solidly into the number 2 slot over Java over the last year. There's no doubt that C is still popular in terms of what people are using for current applications, for the things that are being built and maintained today. But I would actually posit that if we looked at the data another way, we might find a different indicator. Not what people are using, not what they're actually working with today, because that doesn't align to the opportunity in the future that I was talking about, but what people are learning, what they hope to use in the future. Because I think what the languages that people are learning, pursuing, the things that they're chasing in their free time or as a part of their first jobs, or those that are in boot camps and looking to get into technology, that's the best indicator of where the long-term opportunity lies. And here the data are clear, because based on an analysis of where people are searching for language tutorials, Python is the clear favorite. Like, it's not even close. When you're looking for tutorials on Google, most people are searching for Python tutorials. That's the language that people are looking at. Now, part of it is its broad applicability, right? Because Python is already a language that can and is being used in a number of areas, from web development to machine learning, data visualization, game development, and more. It's also becoming the most popular language for inducing coding to students new to programming, from kids to adults. I've taught my kids Python. They're 12, 11, and 7, and that's the language that I started with. Even though I have a background, most of my career as a web developer, and a bit of a bias towards JavaScript, Python was the language that I chose because of just how broadly applicable it can be in a number of different cases. So if we're looking to pin down the next generation of IoT devices, how they can be built and what they'll run, I really think we should look no further than Python, right? Because this is, again, the language people are learning. It's where the opportunity lies, and the easiest way to get people into this space to understand how to work with embedded and IoT devices. So with that as a frame, I've sort of made the case for Python and why I think it's important to pay attention to. I do want to spend a couple of minutes to talk about why Python matters for devices specifically, not just the language in general, but why I think this is interesting if you're doing embedded and IoT development. If you're a C++ programmer and you're still skeptical, bear with me on this, because I think there are a couple of interesting features of Python that at least make it really interesting to pay attention to and to start playing around with. The first is that when you're working with Python on devices, there's no compilation. It's an interpreted language, and that's true on the desktop, and it's true on embedded devices as well. It's true on single board computers. It's true on microcontrollers. You're still working in an interpreted environment, and when you're working with Python on an embedded system, you're actually working in a binary that was written in C or C++ that exposes a Python interpreter for you to use. So you still get to actually embrace the power of Python really in everything that you do. One of the advantages of that, and I'll show you this firsthand in a little bit, is this live debugging through the Python REPL, the read eval print loop. Now, this to me is one of the most mind-blowing aspects of Python on devices, because you're gonna get to see it. Having a REPL on an embedded device means that you can actually interface with the hardware live in real time, inspect it, and what's basically a running application. which historically in the world of embedded development has not been easy or straightforward to do. You also have the opportunity with Python to do machine learning on single board computers. I'm not going to demo any of this today, but I do encourage you to check this out. There's some great companies out there. Edge Impulse is one of them. Check them out at edgeimpulse.com. There are a lot of great resources out there for actually using, doing TinyML, using TensorFlow Lite, and other sort of languages and frameworks on single board computers and being able to do so in the context of Python. And that's pretty exciting. And then finally, it's Python, right? It's an easy language. It's easy to get started with. You don't have to invest 3 months of your life to understand the basics of using it. And it's an elegant and actually quite fun language to learn. So even if you're still skeptical at the end of this, I encourage you to check it out, because Python is an interesting way to get started with this space. So with that as a frame, let's talk a bit about Python variants, because one of the things that's important to understand if you are interested and wanting to get into exploring Python on embedded and IoT devices is to sort of understand that there's a few different flavors of Python that you'll come across. The first is CPython, OG Python, the original. This is the same Python you use in a desktop environment. And if you're working on a single board computer like a Raspberry Pi or a Jetson Nano or Google Coral, this is the Python that you can use. It's the exact same thing that you'd use in a desktop setting if you're doing ML work, if you're doing web work, API work, whatever it might be, the same Python. The one caveat I'll give you, if you decide to go grab a Raspberry Pi, pull out a Raspbian or Debian distribution and install it, is to watch out for Python 2.7. I think we're nearly out of the woods on this, but there are still some Linux distributions that ship with Python 2.7 by default, and you're going to have a bad time if you spend too much time messing with Python 2.7. So with that as a frame, let me actually get into the first demo. I've got 4 different demos for y'all today, so you don't just have to listen to me share slides, but I'm going to actually very briefly stop sharing my screen and switch over to the video on my desktop so that you can see what goodies I have to share with you all today. I'm going to start with this. This is a Raspberry Pi. It's got a device plugged into the top that I'll talk about in a little bit, but simple Raspberry Pi 4. It's a good thing that I bought this thing months ago, because apparently you can't find them anywhere right now. Maybe that'll get better next year. But what's connected to it is a Bosch BME 680, which is a temperature, humidity, pressure, and gas sensor. I'm using effectively the same sensor for all these demos, but that's what's connected in here. So again, I have a single board computer device, and I'm connecting connected that to my Raspberry Pi, and I'm going to actually show you how I plan to control it here in a moment. So let me turn my screen sharing back on. And the first thing that I'm going to do is I'm going to SSH into my Raspberry Pi. There we go. So I SSH in. I have heard that the screen there is actually kind of small, so hopefully I've made the font big enough here for you all to be able to see it. So I'm SSH'd into the Raspberry Pi that's connected to my home network, and I'm actually going to I'm going to move into the directory that I have with my demo. There's just a couple of things in here. There's a main.py and an env folder, and if you haven't worked with Python much before, there is a feature of Python virtual environments, which is very similar to using a virtual environment in a virtual environment package in Node or Ruby or another language like that. It just gives you the ability to have a clean pointer towards Python and multiple distributions and things like that, especially dependencies and whatnot. So if I can spell activate correctly, I'll run that. So I've set up my virtual environment, and I'm going to show you my main.py file. This is pretty straightforward. There's not much to it. If you work with Python before, you'll understand the syntax. But very, very quickly, I'm importing a couple of libraries that are very particular to the hardware side of working with my Raspberry Pi. Board and Bus.io are 2 libraries that give me the ability to access some of the hardware that's physically connected to my board. Bus.io gives me the ability to instantiate buses like I2C and SPI. If you've not worked with those buses before, the basic principles are most microcontrollers and single board computers provide communications buses for you to be able to chain multiple devices together and speak to them all in a very clean way without taking up pins on the board itself. So I've imported both of those, and I've also imported a library for this Adafruit, for Adafruit BME680, which is that temperature and humidity sensor that I'm using. At that point, then the real work for initialization is just to bring up a new instance of the I2C bus. This is connected to a couple of clock and data pins, and without needing to go into the specifics there, the basic idea is that just gives my application a pointer to the way of communicating with that device, so that when I do tell the library I want to get a new Adafruit 680 sensor, that it knows where to go in order to get that, and then it passes in the actual address. From that point, then that's my setup done. From that point, then I move into a loop. This is my sort of infinite running loop here with my while statement, and all I'm doing is just grabbing the temperature and humidity from the sensor and then printing those out to the console and sleeping for 5 seconds. So relatively simple. You're going to see a variant of this exact thing with all of my different demos today, just so you can sort of see some of the language differences. But this is straight up Python. This is the same Python you'd run in the desktop. If I had the ability to get a sensor connected to my Mac, I would be able to run the exact same demo without any changes. Now, I'm going to exit now, and then I'm going to now run the application, main.py, if I spell Python correctly. And you can see now it's 25.5 degrees Celsius and 42% humidity in my office. So it's nice and warm here, and that's it. So very simple. That's running that, calling the sensor every 5 seconds, and actually pulling that out for me and displaying it to the console. So that's the first demo. That's regular Python. Another variant that you will want to pay attention to or be aware of is MicroPython. Now, MicroPython is a Python 3 implementation. So the other two variants that I'm going to share are based on Python 3, not Python 2.7. So they're not necessarily all up to date with like Python 3.9 or 3.10 language features, but by and large, you're going to get everything 3 above in there. This is a Python 3 implementation that's optimized specifically for running on microcontrollers, and it has a number of canned and baked in libraries that come with the distribution itself that allow you to do things like work with hardware pins and things like that. And it has great support on the ESP32. ESP32 is a $4 microcontroller that has Wi-Fi and Bluetooth built in. Definitely worth checking out if you're looking to get started with MicroPython. Or the Raspberry Pi Pico, which was a device that was announced earlier this year. So that is going to be my second demo. I'm going to stop sharing my screen again very briefly, switch back over to my desktop, and this is the device that I'm going to show you a demo for right now. This is the Raspberry Pi Pico, created by the Raspberry Pi Foundation, same as the main Pi SBC itself. And this is also connected to, it's a different style, but this is connected to a very similar Adafruit BME680 temperature and humidity sensor. So I'm going to plug that in and switch back to my desktop. So I'm going to leave the video on here for this and just go back to sharing, because I do want to show you something specifically on the device when I go through this. So I'm going to switch now actually to Visual Studio Code. If you're working with MicroPython or even CircuitPython, you can use Visual Studio Code as your editor. There are a couple of great extensions that allow you to do that. I'm working with one for MicroPython, and having that allows me to actually open up the command palette and run my current sketch, or my current file, Python file, which I'll show you here in a second, but to connect directly to the device. What's really cool about this, you'll see in a second, is what's happening is Visual Studio Code is actually connecting to my device and opening up a REPL for me in order to mess with it. And I know that I'm on the REPL because it's MicroPython Raspberry Pi Pico with the RP2040. So I am in the REPL physically connected to this tiny little device on my computer, which is really cool. Because I'm in the REPL, it actually allows me to do things like import objects. So I'm going to import from the machine library, which is one of the built-in MicroPython libraries that gives me the ability to interface with the hardware. So I'm going to import the pin, if I can spell it, And then I can actually use the dir command. The dir command in Python gives me the ability to see all of the properties and methods on an individual object. So if I do dir pin, I can actually see class name, value, in, out, open, drain. It actually gives me, this is a representation of an actual GPIO pin on my device. I can also import other libraries like OS. OS is a common Python library, and there's an implementation in MicroPython as well. So if I do os.uname, so I can actually see what's in there. I can do dir os. We'll do that real quick first, so you can actually see some of the information that's in there. I can actually inspect the file system on my microcontroller. There is a virtual file system that gets mounted with this. And if I do os.uname, it'll actually give me information about my device. Again, Raspberry Pi Pico, the version that it's running, sysname and node name, all that good stuff is in there. If I do something else like os.listdir, it'll actually show I have a boot.py, lib, and main.py, and those are files. That's actually part of every MicroPython distribution, is that when you actually connect to your device, you have a main.py, which is your actual main application, boot.py, which runs once when the device starts up, and lib is where all of your libraries and dependencies actually are. But it gets even cooler than this, because I can actually go beyond just what I'm doing now of just inspecting the device, but I can actually start to do things interactively with my microcontroller without compiling, without reflashing a new piece of firmware or anything like that. So what I'm going to show you now, I think my screen is, I know, probably pretty small, but watch this. It's actually kind of neat. I can actually get a handle to the LED pin. Every one of these microcontrollers has a set pin definition, and there's an LED on the Raspberry Pi Pico that's tied to pin number 25. So that's my way to actually get a reference to it. So I can do LED, and then with the pin, instantiate a new pin object with that LED pin and set it as an out pin. It basically means I'm writing to the pin, not reading from it. And I can now that I've done this, I can dir the LED, and I can see I have a value method, high, init, low, toggle. I have a couple of different things that I can actually do there. And this is the part where it gets kind of exciting. So if you can see my screen, still see the view of my desktop, take a look at the screen while I do this. If I do led.value and set it to 1, it's a binary pin, digital out, 0 is off, 1 is on. And I say LED value 1, that actually turns on the LED that's on my desktop. So hopefully you can actually see that. If I say LED value 0, it turns it back off. You'll notice that there's a couple of other shorthand methods that do a very similar thing. LED high will turn it on. Again, LED low, just to prove to you that this isn't canned. LED low off. LED toggle gives me basically on or off, depending on how I run it. So to me, this is one of my absolute favorite parts of working with Python on microcontrollers, is the mind-blowing nature of being able to interact with a running device while it's actually running. I'm not doing step debugging necessarily. I'm not doing break and continue. I am literally connected to this device. I am inspecting its state, and it's responding to me in real time. I can't get enough of how exciting that is. Now, when it comes to actually running an application, I mentioned there is a main.py that's part of this. I want to walk you quickly through what this looks like for MicroPython. I have the exact same application here, where I'm gonna basically just read from the temperature and humidity, read from the sensor to get temperature, humidity, and then write it out to the console, write it out to the terminal. And really, there's only a few differences here. The time library in MicroPython is called utime. I mentioned you've seen the machine library already. That gives me access to the pins and the I2C bus. I'm importing a very similar version of the Adafruit BME 680 library. One difference I am doing here is I'm actually toggling the LED pin on and off when I read from the sensor and write it out. And then same thing, I'm just connecting to the I2C sensor. And then in my while loop, same as before, I'm reading from the temperature and humidity, writing that out to the console with a format, turning the LED off, and then sleeping for 5 seconds. So it is literally the exact same application with just a few differences. And so in MicroPython, the way that I now run this is I basically just restart the app with Control-D, do a soft reboot, and you'll see temperature 24.7, humidity 46.3. always interesting to me to see these sensors. They're the exact same Bosch part is on both of these, but I get a little bit of variance from one to the next. It's always kind of an interesting thing, but directionally the same. I'm getting a reading on temperature and humidity there, which is pretty neat. All right. Now let's talk about CircuitPython. For the last demo, the second to last demo, I want to show you CircuitPython. There's definitely a lot of confusion out there for people getting started on the difference between MicroPython and CircuitPython. CircuitPython was forked from MicroPython by Adafruit. And the reason why it was forked was to focus on ease of use for beginners and also see Python compatibility. There's also a little bit of contention over library support, peripherals, things like that. But there is still sort of active collaboration between the two teams. So it's not bad blood or anything like that, at least as far as I understand. And it is actively supported and developed by a team at Adafruit. What's cool about CircuitPython is there's really great library support across a number of different peripherals and devices. Tends to be a little bit less so across MicroPython devices, although there's good utilities for porting CircuitPython libraries into MicroPython, et cetera. And there's also a ton of great board support for Nordic, for the Nordic chipset, for STM, and for SAMD microcontrollers. So there's a ton of variety in terms of the kinds of devices that you can get support for. You can actually see that at circuitpython.org, which I will show you really quick. It's sort of interesting. If you go to circuitpython.org, you can actually see the number of boards that are supported. Everything from, again, the Raspberry Pi Pico, which I just demoed, a number of different Adafruit boards, Itsy Bitsies, the Feather NRF52840, which I've used a lot. A couple of boards from Seed. There's a ton of different devices that have official support for CircuitPython. So it's an interesting language. I'm actually going to show you a board that I'm a bit biased by because it's one that my company, Blues Wireless, just released a couple of months ago, and that's called the Swan. We built the Swan as sort of a low-power, high-performance microcontroller. It runs an ultra-low-power ARM Cortex-M4. It's an STM32-based microcontroller, which is a chipset we're pretty partial to. We like the STM32L4. It runs on one of our core devices as well. And it has 2 megs of flash and 640K of RAM. One of the reasons why I'm sharing this, though, is because we built this microcontroller as a polyglot microcontroller, basically. We support C, C++, Python, CircuitPython, and Arduino. And those are all supported in that exact same board. I mentioned ML a couple of times today. It's also, if you're looking at doing edge ML on devices, it's also an MCU that's great for that because it's got a fast clock for a microcontroller and a lot of RAM and flash for running tiny ML models and lots of pins for complex peripherals. So, but enough of that short pitch there. I just wanted to give you the frame before I actually demo this device. So for the last time, I am going to stop sharing very briefly. Oh, actually, you can still see my desktop, but I'll just zoom back in. This is the Swan. It's connected to this board here on the top. This is a Feather form factor device. It, again, is connected to a Bosch BME 680. So same device, same demo. I'll show you that here for just a sec. So let me switch my video back, share my screen again. And this time, what I'm going to do is I'm going to pull up a different IDE called Mu. The Mu editor is a Python editor. It actually works with desktop Python, MicroPython, etc. All that good stuff. Let me actually load. Nice. Hold on. Move some things from here because I forgot to remove a few minutes ago. I'm not getting to any of this stuff just yet. But just to show you the simple, again, very, very simple demo, effectively the same thing that we're running right now, or that we ran on the MicroPython device. I'm importing, and again, this is CircuitPython, so there's a few differences. I'm importing the board library. Board gives me access to I2C, so there's not a machine library in CircuitPython. There's board IO, bus IO, different libraries that give you the same access, but they're named slightly different. But functionally, it's exactly the same, right? I'm instantiating an I2C instance of my I2C bus, connecting to the Adafruit BME, and then in my loop, reading the temperature, humidity, writing it out, sleeping for 15 seconds. I'm going to change that to 5, and I'm going to save. And I can also open up the serial terminal here from Mu, which is nice. It gives me the ability to actually do the same sort of thing I was doing in Visual Studio Code, to see the REPL, to reload, et cetera, all that good stuff. So again, temperature 24, humidity 45, and this will actually run every 5 seconds. So there's not really anything different about that, just minor language differences between the two different boards. So let me disconnect from that for the end. The last little piece here, I did want to spend some time talking about the Internet of Things, right? Because everything I've showed you so far is just working locally with a microcontroller, doing something in a completely offline way. And while I recognize that not every embedded application is a connected application, more and more of the devices that we're building do rely on some sort of internet connectivity. So it's really common to ask that question of, if I'm going to use Python, how does this impact me as someone that might be working with IoT sorts of applications? And there's really good news for the Python world here, is because there's an increasing number of IoT vendors that are building not just for C and C++ developers and Arduino developers or write your own ASIC sort of developers, but working with the Python developers and those on the Pi and embedded systems as well. One example of this is my company, Blues Wireless, and we provide an agnostic way of connecting sensors and applications to cloud services with what we refer to as a cellular device to cloud data pump. And that starts with a product called the Notecard, which you've seen a couple of sneak peeks of on my desk. It's a low power cellular and GPS module that comes with cellular IoT connectivity in over 135 countries. The device comes with 10 years and 500 megs of data baked into the cost of the device. There's no monthly data plans, no activation fees. The price is on the tin, as they say, so you don't have to worry about a ticking clock when you start your project. This is one of the things that I love about it. I build a lot of prototypes with a note card because I'm not paying a monthly fee. It's just there included with the cost of the device. And it's also super developer friendly in the sense that whether you're Python or C or Arduino or what have you, is that the API for the device is 100% JSON commands. So you can use JSON to do everything from configuring the device and its GPS location to adding sensor data and more. Literally, everything happens through working with a JSON API. And so what we like to say is that if you're adding the note card to a Python or other based application, is that you can go from unboxing to sending any bit of data you wish to the cloud in minutes via a secure cellular connection. And security is important here. Every note card actually includes the keys for making a connection to our cloud service baked into the device at the point of manufacture. So there's literally no key rotation or cloud provisioning process. You just power it up and start sending it data, and it knows exactly where to go to phone home. And as for where that goes to phone home, that's notehub.io, which is a cloud service I'll show you in just a moment. It's ready and waiting for project data once devices come online. It's designed to be a really thin middleware between the note card and your own cloud application, so we make it really easy to route data out to AWS, Azure, GCP, or a visualization service like Ubidos or Datacake or Losant, what have you. And because that's really the fun part, right? The whole reason that we build IoT devices is for this. It's for the visualizations, to see where assets are, to understand how we can actually make business decisions, just sort of see insights from these devices. We add internet to devices not just because we can, or at least we shouldn't be anymore. Hopefully those days have passed, but we're doing it because we need answers, because we want to make decisions out the other end. And so we really think that with a note card that you can really focus on not having to worry about connectivity, but just doing interesting things. And we have folks in our community and our team that have done things like working to measure water quality around water treatment facilities, or measuring air quality at schools and public spaces, or monitoring physical assets regardless of where they're located. And a lot of these things have been built with Python as the language that's actually controlling the host and the microcontroller. We're not just device agnostic, so I'm not just sharing this because I'm like, hey, you can use Python and talk to our device, but we actually actively support the Python developer experience through a complete SDK. We have a Python SDK that works out of the box with CPython, MicroPython, and CircuitPython. So if you're using any of the variants that I've shown you demos of today, we have the exact same SDK and library that makes it really easy to interact with that device and send JSON requests and read things from the other end. So that's the last demo that I'm going to give you today. You noticed I showed you my desktop already. And you may have noticed when I showed you the Swan, when I showed you the Raspberry Pi device, that the Notecard was plugged into the top of both of those. It's connected with a product that we call Note Carriers, which just facilitates a connection between the two. And really all I want to do here in this case is change up my program a little bit to add that connectivity between the Notecard, between my Swan, my CircuitPython device, and the Notecard. And so the program gets a little bit more complicated here, but what I'm ultimately going to do is import another library. That's our Notecard, our Python Notecard library. I'm going to set what we refer to as a product UID, and the product UID is basically just an assignment between the Notecard and our cloud service notehub.io. So when the device comes online, it automatically connects to the cellular network and our cloud service, but this product UID gives that association, so your project, your application is the one that receives that data. Otherwise, it doesn't really know where to go. Just as before, I'm starting a connection to my Adafruit BME 680, and then I'm opening a connection to the Notecard here. And then from here, what I'm doing is I'm using our library to send a couple of different JSON requests. I mentioned before, it's a 100% JSON API. And so I'm basically just creating dicts in Python, one for what we refer to as hub.set. Every request you send is effectively, performs some sort of action on the Notecard side. Hub.set is the way I can configure my Notecard to sort of run where it needs. I tell it where to go on the cloud side, tell it what sort of connection to have. I can tell it how often to synchronize with the cloud service. There's a lot of different features that are in there that we have all documented in our dev site. So in this case, I'm just giving it that product UID, and then I'm also telling it to maintain a continuous connection. So it maintains an active, once it gets that cellular connection, it maintains a continuous connection to the cloud, to my Notehub project, so that I can send up data on demand. Then from here, there's no difference here in how I'm actually reading the information from the device, but when it comes time to actually send that data, what I'm going to do is use a different API called note.add. And note.add is basically the method by which I tell the Notecard where I want my arbitrary data to go. So when I send data to the Notecard that I want to end up in my cloud service, I do so by adding notes to note files. That's sort of our concept for how we organize the data that you send. And the body of a note can be anything that I want it to be. That's user-defined arbitrary data. So in my case, I just want to send the temperature and humidity. That's the JSON payload, the body that I'm sending along to my application. So I send that to the Notecard, and then I go back to sleep for 15 seconds. So I can, just as I did before, I'm going to save this to my device, and then I'm going to restart the REPL. And you'll see now a couple of different things. One is, because I'm running in debug mode, you can see the actual request that goes to the Notecard. The hub.set with a continuous mode, again, it's just a JSON object in the background. There's a product UID, and then there's a couple of other things that we send along for the ride when you make that first request, which is what we've kind of referred to as like our browser user agent. We have a detection for what operating system, what version, the platform family, so that we can have insights on our end with the kinds of microcontrollers that people are developing with, and potentially support those sorts of use cases in the future. And then after I pull the temperature and humidity, all I'm doing is I'm adding that and then syncing directly to the cloud service. And so again, my application is running. I'm doing the exact same thing I did in every other demo, but I've added internet to this one by bringing the Notecard and sending it off to our cloud service. And the way this looks on the other end is, if I go to notehub.io, I have an account and I have a bunch of different projects. And there's one that I have down here towards the bottom called temp sensors. And when I pull this one open, you can see I have a number of different devices. This is the one that I am running right now. It has my location. I can see that it's online, and then I can actually go into the events view in NoteHub and see the data that's coming across. So I actually just got a note that came in. This is its body. That's the temperature and humidity that I just sent along. And this is its full-on JSON. From here, what I'm actually able to do is then route that out to my own application. I didn't build that. I don't have a demo of that for this talk, but just to show that's the whole value of this piece of the puzzle, is that I can very easily get data into a place where I can then turn around and route it into another location. In this case, I have just an MQTT server configured on the other end. So it's moving an MQTT. If that's something you like to do, I can send it into AWS or Azure or something along those lines. So to wrap up today, I just wanted to offer a couple of different resources, and then I'll happily answer any questions that might have come up. I'll check the online feed, and I know there's a mic in the room, so I can answer any questions. But if you're looking to do more, if you want to learn about Python, try it out in one of your next applications. There's a couple of different resources. CircuitPython.org is the official site for CircuitPython, MicroPython.org for MicroPython. If you're interested in trying out the new Raspberry Pi Pico and their RP2040 chip, there's a getting started resource here. And then finally, if you're interested in trying to do some IoT work with Python, you can check out our developer site at dev.blues.io. If you are interested in checking out the Swan or the Notecard, you can actually grab one of those at shop.blues.io. We also have our products on SparkFun and DigiKey, if that's more your speed. But that is what I had for slides today. So let me actually check and see if there's any questions online. And I know there's a mic, so if anybody has questions to ask, I'm happy to give my voice a break and hear from you all. Aha. Okay, I did just have one question come up online. Somebody that noticed my 3D printer in the background. Will there be a 3D printer running Python? Oh, there's surely there should be sometime soon. Yes, I have a Prusa 3D printer. I love this thing. Highly recommend it if you're interested in getting into 3D printing. But I have not yet tried to hack the microcontroller that's running on that Prusa. But I'd be willing to bet that if you looked up 3D printing running Python, that somebody is working on it for sure. That's the beauty of this space, is that there's always somebody tinkering with something. Right. All right. Well, thank y'all so much. I really enjoyed. I'm glad I had an opportunity to speak to y'all today, even virtually. And next time around, let's do this again in person, and I'll be there. I'll be there with y'all. Thanks very much.